Hi, everybody. Hi, Geneva, and the people who have joined us. Camera's over there. And hi, anybody on YouTube. Welcome to the first talk of the year. And I'm very happy that we have Emily Adlam here, who's going to talk to us about entropy bounds.
Hi, everyone. Thank you very much for coming, and thank you for the invitation. It's great to be here. So I'd like to talk about this paper, Entropy Bound Epistemic. And I've been told that when there's a put a question in the title of a paper, the answer is usually no. But in this case, the answer is genuinely, I don't know. I'm not sure what the answer to this question is, so I'm not going to tell you what the answer is in this talk. I'm just going to try to explain what I mean by this question and why I think it's interesting, and sort of follow up what the consequences of the possible answers might be. And I hope that at the end you will tell me what you think the answer is, and that will give me some more insight. Right, so yes, I will begin by giving some background on the entropy bounds. So apologies if you already know everything about them. Then I will talk about two different ways of interpreting the bounds in terms of the light sheet postulate versus the surface postulate. I'll give a general discussion of the problem of learning about different sites and space-time region, which is going to motivate the possibility of epistemic views of the bound. I'll contrast that with possible ontological views of the bound. And finally, I'll say something about how all this is connected to gravity. So the saga of the entropy bounds has its origins in this original result due to Wittgenstein and Hawking, who conjectured that the entropy associated with a black hole of surface area A is given by S equals A over 4GH bar. At the time when this conjecture was made, it was quite speculative and was quite controversial, but since then we have gathered quite a lot of theoretical evidence that this is indeed the correct entropy for a black hole, most notably the Hawking radiation temperature, which has been shown to be the exact temperature that you would expect for an object of this entropy. And so although there's still sort of empirical observations backing this up, there's certainly a strong theoretical case that it's the right entropy for a black hole. So this also has some consequences for what we should say about the entropy of other objects in regions of space-time. So in particular, Wittgenstein noticed that if you start lowering systems into black holes, then in general, if you're not going to violate the Wittgenstein-Hawking entropy value, you need that any system you lower into a black hole has an entropy which is less than or equal to 2 pi ER over h bar, where E is the energy of the object and R is its radius. And it can be further shown that, at least for a weakly gravitating system, this reduces to a bound S is less than or equal to A over 4GH bar, where A is the surface area enclosing the object in question. That obviously looks similar in form to the Wittgenstein-Hawking entropy. It led to a fairly bold speculation to the effect that maybe this is just true for any region of space. Maybe for any region of space you take whatsoever, it's going to have total entropy less than or equal to A over 4GH bar. So this, if true, would be quite a striking result. For a start, you might be surprised to learn that regions of space-time have any finite entropy bound at all. If you think of space-time as being continuous and potentially able to be filled up completely with degrees of freedom, you might think that the entropy could potentially be infinite. But even if you did have some reason to expect a finite entropy, if, for example, you thought space-time was discrete and so there's limited spatial information storage, you still should be surprised by this result, because probably the natural and obvious thing to expect is that the entropy content of a region of space-time would scale with its volume. So if it really scales with the surface area instead, that's quite a striking result, and seems possibly to be telling us something quite novel about space-time and its content. To some extent, we can explain this by noting that if you put too much energy into a region of space, it's going to collapse and form a black hole. And so this total state space of a given region of space is going to be less than one might naively have thought without taking that possibility into account. But nonetheless, the fact that it supposedly has this bound that is exactly proportional to the surface area seems very notable and potentially important. Now, it turns out that this strong bound is not exactly right for all systems. In particular, it can be violated for systems which are undergoing some kind of quite rapid change of the structure of space-time. So, for example, in cosmic inflation, gravitational collapse, and so on. But Raphael Rousseau has suggested a covariant generalization of it, which does seem to be, as far as we currently understand, pretty much universally true in our universe. So that's the covariant entropy bound, or Rousseau's bound. It has the same form as the strong entropy bound, so S is less than or equal to A over 4GH bar, but the entropy is now defined on a light sheet rather than on the spatial interior of the surface. So a light sheet here is defined by, you take your given surface, which has area A, and then you imagine a set of null geodesics leaving the surface orthogonally with zero or negative expansion, and you follow them up until they intersect at what's called a caustic, or they meet a singularity. So for example, if your surface is just a sphere, you're going to have, you can imagine that null geodesics leaving the surface as something like light rays projected from the surface at a perpendicular angle. And there's going to be 4 possible families of such null geodesics. You can have light rays going out of the sphere into the future, out of the sphere into the past, into the sphere into the future, and into the sphere into the past. So of those 4 families of null geodesics, the ones going out of the sphere are going to have positive expansion because they're getting further away as they leave the sphere, but the ones going into the sphere are going to have negative expansion. They're getting closer together as they move away from the surface. So the light sheets of the sphere are going to be those 2 families pointing inside of the sphere, one going into the past and one going into the future, and they're going to follow each of those families until they intersect, which of course will occur at the center of the sphere. So this example also shows nicely why it is that the covariant bound reduces to the strong bound in many ordinary cases, because you can see that a family of light rays going into the sphere is going to traverse the entire interior of the sphere exactly once if nothing funny is going on inside. And therefore, apart from in cases where you have some kind of strange gravitational collapse happening inside the sphere, you'd expect that the entropy they get from integrating over the whole path of those light rays will be the same as just the state on any space-like slice of the sphere. So that's why those two results look the same in many ordinary cases. So Rousseau's bound is surprising in much the same way as the strong entropy bound is. It again seems to suggest that the regions of space-time have less entropy or information content than we might naively expect. And again, it's perhaps surprising that this bound, if correct, ends up being exactly proportional to the surface area. So the strong bound and the covariant bound led to a number of speculations to the effect that maybe the number of degrees of freedom inside a region of space-time is limited in this particular way. But there are some reasons to be cautious about this kind of claim, in part because entropy as used in the entropy bounds doesn't really straightforwardly correspond to a number of degrees of freedom. The idea that entropy is in some sense counting degrees of freedom seems to be coming from a sort of information theoretic notion of entropy, like the Shannon entropy, because it is true that when you're looking at the Shannon entropy of systems, that does in a sense count the number of sites for information storage or degrees of freedom. For example, a system, if you have a system producing bit strings of length n, then the maximum entropy of those bit strings is going to be n. So in that sense, we do seem to be counting degrees of freedom or sites for information storage. But the entropy is featuring in the Bekenstein-Hawking bound, and hence presumably in the generalizations of it in the form of the entropy bounds, seem to be mostly thermodynamic rather than primarily information theoretic. Bekenstein himself did seem inclined to interpret the Bekenstein entropy in an information theoretic way, but most of the evidence we have for it seems to be thermodynamical. Certainly the Hawking radiation temperature is a thermodynamic argument, and similarly arguments concerning exchanges of energy across the surface of the black hole seem to be thermodynamic in nature. And although it is true that in many sort of ordinary situations, you can sort of map thermodynamic entropies to an information theoretic entropy based on some count of the number of states, since we don't have an independent grasp of the state space of a black hole or an arbitrary region of space-time, it's not clear that we can straightforwardly assume that the thermodynamic entities that are relevant here can be thought of in these information theoretic terms as counting degrees of freedom. There's a further problem in that the thermodynamic entropy is often thought of as being observer dependent. It depends in some sense on a choice of coarse graining or choice of exogenous variables, or what what the observer has in terms of their ability to manipulate and change the system. So in that sense, one might worry that if the entropies featuring in this bound are observer dependent, it could not be the case that this bound is telling you some sort of objective fact about the number of degrees of freedom in the region. However, Flanagan, Merrill, and Wold are aware of this problem in their discussion of the entropy bound, and they argue that although there seems to be a tension between the fact that these statements are claimed to have the status of a fundamental law or a fundamental assertion about the number of degrees of freedom, that may seem to be in tension with the idea that entropy is a quantity whose definition is coarse-grained dependent. But this tension is resolved by noting that the number of degrees of freedom should be an upper bound for the entropy S, irrespective of choice of coarse graining. So the thought here is simply that even if the individual entropies that are bounded by the bound are observer dependent, nonetheless the bound itself could potentially still be an observer independent fact about the system, and indeed the number of degrees of freedom would be a reasonable choice for a sort of universal bound that should apply to all observers, no matter their choice of coarse graining. So although there are questions still about whether we should think about the bounds in terms of degrees of freedom, I think there is at least some case to be made that this does make sense. And so for most of the rest of this talk, I will suspend disbelief and assume that there is some interpretation in terms of degrees of freedom available to us and try to understand what that might look like. So the big question, if we are going to think about the entropy bounds in terms of degrees of freedom, is where are those degrees of freedom? Which region of space-time does it count degrees of freedom in? So in terms of the covariant bound, perhaps the most natural conjecture is to say, well, the entropy is giving us a count of the number of degrees of freedom on the light sheet. That seems to be what Busso has in mind in his discussion. So that would suggest that for a given light sheet bounded by a surface of area A, the number of degrees of freedom on that light sheet is going to be equal to A over 4GH bar. So that seems to make sense given that we obtain this entropy by integrating some kind of entropy fluid or something like that over the light sheet. But on the other hand, some people have questioned this interpretation. So in particular, Lee Smolin and also Raphael Sorkin and Carla Ravelli to some extent have argued that perhaps we should think about at least the Beck-Steinhorn entropy, not as counting degrees of freedom on the interior, but as just counting the degrees of freedom on the surface that bounds the region. So that would lead to the suggestion that actually all the entropy bounds tell us is that the number of degrees of freedom on a surface of area A is A over 4GH bar. And the reason for that they make this suggestion is basically that all the arguments for these entropy bounds concern exchanges of information and entropy across surfaces. And so the claim is that we shouldn't think about them as telling us something about the interiors, we should think about them as telling us something about the surfaces. But if the surface postulate is really the only content that the information bounds has, that the entropy bounds has, that makes them seem rather less interesting and somewhat disappointing, because the thing that was supposed to be interesting about the entropy bounds was that there seems to be much less entropy content in various regions of space-time than one can naively expect. Whereas just saying that the entropy on a surface is proportional to its surface area seems much less surprising. As soon as you have any reason to think that the entropy on a surface might be finite, might have a finite bound, you would probably be inclined to suggest as your first conjecture that that bound is going to be proportional to its surface area. So if that's all the entropy bounds are telling us, they seem much less radical and interesting than at first thought. But I'm not totally convinced that the surface postulate can be the full content of the entropy bounds. The issue here is that if the surface postulate were the real content of the bounds, it would seem like it shouldn't matter all that much how you specify the interior. So regardless of whether you specify the interior in terms of a space-like slice, as in the strong version of the bound, or in terms of a light sheet, as in the covariant version of the bound, it would seem then that it really shouldn't matter which of those you choose, because the real content of the bound would be in what is said about the surface, which is the same between those two formulations. And yet it seems like we have pretty good evidence to the effect that the strong version of the bound is not true everywhere in our universe, but the covariant version of the bound does seem to be true everywhere in our universe. So that the presence of that evidence seems to suggest that there is a meaningful difference between those two formulations, which therefore seems to suggest that the bound is telling us something about the interior regions that are bounded rather than just the surface. So that gives some reason, I think, to think that if we are going to interpret entropy bounds in terms of degrees of freedom, the light sheet postulate may indeed be the right one. On the other hand, the surface postulate has a lot of independent support. As I say, if you're going to believe that there are bounded degrees of freedom on a surface, you would naturally think that that should be proportional to their surface area. So that leads to the suggestion that maybe both of these postulates are true. Maybe the number of degrees of freedom on the light sheet is A over 4G H bar, and also the number of degrees of freedom on the bounding surface is A over 4G H bar. But if that is the case, if they're both true, that seems like quite striking and surprising. And it seems as though we would want to have some explanation for why there should be this notable relation between the degrees of freedom on a bounding surface and the degrees of freedom on the light sheet that it bounds. So if we are going to make that conjecture, it seems like we're going to have to say something more about how those degrees of freedom are related. So I now want to suggest one general way in which they could be related. So first of all, I want to suggest that a sort of natural corollary of the surface postulate, the idea that the number of degrees of freedom on the surface is proportional to A over 4GH bar, this has the natural corollary that the rate at which information passes through that surface should also have a similar bound. That's because, given our current understanding of physics, it seems that information gets transferred in a local way via local interactions, and that seems to suggest that if information is going to pass through a surface, then it needs to occupy degrees of freedom on that surface as it passes through. And therefore, if the number of degrees of freedom available on a surface is bounded, we should then also expect that the rate at which information passes through a surface will be bounded. And exactly how that bound works will also depend to some degree on how you think about time, whether you think time is also discretized, or whether you think information can pass through in a continuous way. But I think that independent of those considerations, it's reasonable to think that there's going to be some kind of bound on the rate at which information passes during an infinitesimal interval or something of that kind. So that then leads me to suggest the following sort of thought experiment. Suppose that you are presented with an opaque sphere with a surface covered in LEDs. And your task here is to find out everything you can about the physics going on inside of that sphere. Moreover, you're informed that the physics going on inside of that sphere is some totally new physics, which is unrelated to known physics. You can't assume anything about it in terms of what you know about existing physics. The only thing that you know about what's going on inside the sphere is that information can only leave the sphere through the surface, and it will do that by sending signals to the LEDs on that surface, which will light up when they receive the signal. So the question is, what are you going to do to try to learn about the physics inside of that sphere? Well, presumably you'll do something like the following. You'll observe the sphere over time, you'll see various different patterns of illumination on the surface, you'll make some note of how the patterns of illumination change over time, and then potentially you'll try to write down some kind of law relating the past illumination states to the future illumination states. Maybe a Markovian law or maybe a non-Markovian law, but some kind of relation between past and future states. And perhaps you might just stop there. And if you do, clearly what you will have arrived at is a description of the states of the sphere in terms of the sphere having no more than n degrees of freedom, corresponding to the number of LEDs on the surface. So if that is your approach, you're going to end up with a description such that the number of degrees of freedom you assign to this whole system is equal to the number of degrees of freedom available on the surface. Now you might try to do something more clever than that. You might start trying to write down models for what's going on inside of the sphere in more complex terms. But since you can only get n degrees of freedom out of the sphere at a time, it's reasonably likely that you're still going to end up with some description assigning the interior n degrees of freedom as well, because you're limited in your ability to get out any more information than that, and also because you know nothing at all about the kinds of processes that are going on inside the sphere. It's going to be hard for you to develop sort of independent inferences about what extra degrees of freedom inside might be doing. So I don't necessarily want to claim that it's completely impossible for you to end up with a description assigning more than n degrees of freedom. One way that might happen is if you see sort of non-trivial correlations between the LED states over time. So, for example, one of the reviewers to this paper asked, what happens if the sphere starts playing the collected works of Shakespeare in Morse code? wouldn't you then be inclined to think that there are more degrees of freedom inside because the collected works of Shakespeare must be stored inside the sphere? So I do think there are ways in which you could ultimately come to have a more complex description, but in that kind of case, it's going to be quite hard for you to notice that the sphere is playing the collected works of Shakespeare, unless you have some kind of prior indication that it might do that. And similarly with other kinds of cross-time correlations, unless you have a sort of strong reason to expect certain kinds of cross-time correlations, those aren't necessarily easy to notice. And moreover, even if you do notice such cross-time correlations, it seems like it would always be open to you to continue saying that the sphere has only n degrees of freedom and to simply postulate some kind of non-Markovian evolution over time. So the upshot of the thought experiment is not that you could never assign the sphere more than n degrees of freedom, but that it would not be very surprising if you were to assign the sphere n degrees of freedom. That seems like a natural consequence of the epistemic restrictions that you are subject to under these particular circumstances. So there's a sense in which, under these circumstances, you end up with a description which gives something like a natural entropy bound that is the result not necessarily of the total number of degrees of freedom inside the sphere, but rather it's a consequence of your epistemic access to the sphere and the limitations on how you can get information out of that sphere. So obviously the point of this thought experiment is that in some sense the sphere situation describes the situation we are all in all the time when we try to learn about physical systems, because information transfer in our universe seems to be local, so we don't interact directly with physical systems, we interact with them through their bounding surfaces. So if there are indeed bounds on how information can emerge through their bounding surfaces, that there's a natural sense in which one would expect that to lead to some kind of bound on our descriptions of their state spaces, since we have to build those descriptions using the information that we can get out from the bounding surfaces. That is, I think, to some degree supported by particularly the covariant formulation of the entropy bound, because at least in sort of special cases, a light sheet looks a bit like the region to which you would naturally be inclined to assign a state if you would collect information simultaneously from some surface. So that is to say, if you imagine that information is propagating at the speed of light and arriving at the surface, then the light sheet, the path-directed light sheet associated with a given surface is going to be something like the locus of where the information all originated from that arrives at the surface at the time that you collect that information. So in some sense, a light sheet looks like an appropriate way to project the information that you have backwards in time to describe the state of what's going on in the interior. So there's a sense then that in which the surface postulate can be thought of as implying a sort of epistemic version of the light sheet postulate. It doesn't entail that the true objective number of degrees of freedom on a light sheet is going to be bounded by A over 4gh bar, but it does imply that the number of degrees of freedom that you can instantaneously get information about will be described by A over 4gh bar. And so that's a sort of natural way of understanding why there should be this connection between the light sheet postulate and the surface postulate. And indeed, I think the relation between them sort of makes an interesting point about the relationship between the way we think about the ontological content of space-time and the epistemology of space-time. There's a sense in which the sort of intuitive conception of space-time as being sort of densely filled up with information content or degrees of freedom in proportional to its volume vastly outstrips the amount of information we have available to us and the evidence we have, because if it is indeed the case that there are limitations on how information can pass through surfaces, then the amount of information we can extract from a given region of space-time is always going to be less than what you would expect the information content to be if it really scales with the volume. So there's this kind of interesting I haven't fully decided what I think about this, but there seems to be something interesting here in terms of how we should think about the ontology of space-time versus what we can actually find out about it. So one objection you might have at this point is that I've talked about the entropy bound thus far mostly in terms of closed surfaces, and so clearly with a closed surface it is indeed true that if you're going to get information out of the corresponding light sheet, it has to pass through the bounding surface. But the entropy bounds are also supposed to apply to open surfaces. Right? I can postulate some sort of screen-shaped object in space-time, and the entropy bound also places a bound on the corresponding light sheet projected backwards or forwards in time from that screen. And you might say, well, the epistemic conception of the entropy bound isn't going to work in that kind of case because, of course, we can get information out of that region without it passing through the screen to go around the outside of the screen. However, you're not going to be able to make use of information that's coming around the outside of the screen unless you already have some independent grasp of the content of the space-time region around the outside of the sphere, the screen, and the physics going on in that region, because otherwise you won't know how to interpret the signals you're receiving from the region you're actually interested in. So that suggests that in order to understand the open surface case, you should sort of extend your screen to cover the full region of space-time that you're interested in getting information out of, including regions where you would allow information to pass around the edges of the original screen, and thus you should extend your screen until all the information that reaches you is required to pass through that screen. And so in that sense, you're still going to have a bound because all the information you can get about the region behind the screen is going to have to pass through that screen. So I do think there's a case to be made that this sort of epistemic conception of the bound does still make sense, even if you're dealing with an open surface rather than a closed surface. Another question you might have about this kind of thought experiment would concern the possibility that, in addition to just passively getting information out of regions, we're usually also able to intervene on them. You might say intervening on them is going to give us more information than you would have if you just passively wait for information to emerge. But I think we can sort of model that in the sphere case by imagining a variation where you're allowed to adjust the degrees of freedom on the surface. So you can switch the LEDs on and off and see how the sphere responds to that. But it seems to me that in that case, since you would have only n degrees of freedom to intervene on, that wouldn't necessarily change the fact that you would end up with a description having n degrees of freedom, because the information you can send into the sphere and seek responses based on is also bounded in the same kind of way. And so the epistemic conception, I think, still works even if you allow interventions. So this kind of conception of the limitations that we have in learning about the content of regions of space-time ties in interesting ways to increasing recognition of the importance of surfaces in modern physics, and particularly in various approaches to quantum gravity. So Crane, for example, made a somewhat similar point about the epistemology of space-time, noting that if we divide the universe into system and observer, the observer no longer measures the state of the system, but only that part of it which impinges instantaneously on the observer. So this led him to formulate a categorical approach to quantum gravity based on the algebras of surfaces. Similarly, Euckel's general boundary formalism is a somewhat operationally motivated approach to quantum gravity, which is based on calculating transition amplitudes for parts of surfaces. So again, it's based on the idea that we're only going to interact with various quantum gravitational systems via bounding surfaces. Similarly, a lot of holography can be understood in this sense. For example, May suggests we should think about holography as the requirement that asymptotic tasks possible using the bulk dynamics should coincide with tasks possible using the boundary. And from an epistemic point of view, it seems in some ways entirely unsurprising that our physics should have holographic characteristics like that, given that we only do interact with the systems we study through their boundary. So one might naturally expect that the dynamics we come up with for them would have the consequence that they're limited to what can be achieved using the boundary. Similarly, I won't go into details here, but various approaches to quantum gravity give a really important role to surfaces. So in loop quantum gravity, for example, the most straightforward way to actually extract some predictions from the approach is to calculate transition amplitudes for classical or classical-ish boundaries with the quantum gravity effects defined to the interior. Similarly, ADS-CFT, where it applies in our actual universe, applies mostly to bounded regions with classical-ish boundaries. So in all of these senses, there's kind of an increasing emphasis on the role of surfaces and the epistemology, the way in which that is linked to the epistemology of learning about regions of space-time. So I think this kind of increasing prominence of surfaces, particularly in approaches to quantum gravity, is one of the reasons why I think understanding more clearly the nature of the covariant bound and the role of surfaces in the story is potentially important for our understanding of space-time. So with all that discussion in mind, here is a sort of classification of various different views that you might take to the covariant entropy bound. I'm assuming here that you A, accept that the bound is correct, and B, do think it has something to do with degrees of freedom. So motivated by the kind of epistemic discussion I've had, I've just given one possible way of thinking about the bound would be to say the bound is merely epistemic. The real number of degrees of freedom on a light sheet may be greater than the amount specified by the bound. And I think there are sort of two different ways you could pursue that view. One would be a more pragmatic approach, which would say, there may exist degrees of freedom beyond those allowed by the covariant bound, but we're never going to know anything about them. Kind of by definition, they don't have an impact on the things we can observe, so let's just get on with physics as if they're not there at all. One could also take a more positive epistemic view, which would say something like, there may exist these extra degrees of freedom, and it may be important to take them into consideration that may have an impact on our understanding of physics, even if we can't directly observe them. Correspondingly, there's also a possible ontological view of the entropy bound, which I think corresponds more closely to some of the original conjectures about the bound telling us about the number of degrees of freedom inside a region of space-time. So that involves thinking about the entropy bound as a constraint on something like the real ontological number of degrees of freedom on a light sheet. And again, there's sort of pragmatic and positive versions of this view available. The pragmatic version would invoke some kind of pragmatism or empiricism to say that since we can't have information about degrees of freedom beyond the covariant entropy bound, we should take it that there just aren't any further degrees of freedom, but the bound doesn't have any deep meaning beyond that. Or a positive ontological view, which would instead say that actually the covariant entropy bound is some kind of fundamental constraint or follows from some aspect of the fundamental ontology, so it can be understood as telling us something quite profound about the nature of our reality. So I think versions of all of these views seem to be espoused in different ways by different people. So in particular, something like the pragmatic epistemic view seems to be potentially espoused by a number of physicists, at least with respect to the special case of black holes. Doherty and Callender, for example, suggest that the way that physicists think about black holes is to say that we talk about black holes as if entropy crossing the horizon vanishes, not because we necessarily think the system itself vanishes or is destroyed, but because the ordinary entropy, once it crosses the event horizon, it's out of sight, it's no longer accessible, we might as well just formulate our physics as if it doesn't exist there anymore. That seems to correspond to the kind of pragmatic epistemic view that I suggested for the covariant bounds, where we accept that there may be additional degrees of freedom, but we just take it that they're not relevant for physics. Kind of in opposition to this, it has been suggested by some people, particularly Smolin, Sorkin, and Ravelli, that it may actually be important to take into consideration the possibility of additional degrees of freedom. So, for example, Ravelli thinks it's important potentially to understanding the black hole information paradox. He notes that the Page argument, which is the argument usually used to argue that there is some paradox involved with the black hole information paradox, the Page argument is based on the fact that if the number of black hole states is determined by the area, then there are no more available states to be entangled with the Hawking radiation when the black hole shrinks. Whereas if we just accept that there are more states available in a black hole, even though they're not accessible from the outside, then it seems as though the Page argument for the information paradox fails, and potentially there is no paradox. So the intuition here is that it may be important to keep in mind that there are these extra potentially inaccessible degrees of freedom, because otherwise we're going to end up in confusions where information seems to mysteriously vanish when in fact it's just become inaccessible to us. So versions of this view, as I say, seem to be espoused by Smolin, Sorkin, and Ravelli. So if we take the epistemic view seriously, what will we expect that to mean for physics? So here I'm just going to put aside everything we know about physics and just ask if we did indeed live in a world in which regions of space-time typically have extra degrees of freedom that are not accessible from the outside due to these limitations on information passing through surface, what would that look like? What kind of phenomenon might we expect to see? Well, I think one thing we should really expect to see in that kind of world is some kind of indeterminism. The inaccessible degrees of freedom are going to play the role of hidden variables, and so processes will look indeterministic to us because we don't have access to the full degrees of freedom, which in fact determine their outcomes. I also think there's an argument to the effect that we should expect to see something a bit like uncertainty relations. To see that, let's imagine some kind of particle which has some small position uncertainty, which is to say we can localize it inside of some small region of space-time. then the limitations on information passing through the surfaces of regions of space-time entail that if the region of space-time is small, its surface area is going to be small, and so the information that can get out of it is limited. So in some sense, as we localize particles more precisely, the information we can access about things like their momentum is going to become smaller and smaller. So we should expect to see some kind of trade-off between position uncertainty and momentum uncertainty. So obviously those are some features of quantum mechanics. So the thing I'm driving at here is potential that this kind of epistemic view of the entropy bound could help us understand some supposedly puzzling features of quantum mechanics. And indeed, more generally, various people like Ravelli have argued in the past that a number of supposedly puzzling features of quantum mechanics can be understood by imagining an ontological theory with some kind of epistemic restriction on it. And this kind of restriction in terms of information passing through surfaces seems like it could potentially play the kind of role of the epistemic restriction that is envisioned by Stickens and Ravelli. So obviously these arguments are somewhat heuristic and hand-wavy, but I think there is potential for an epistemic view of the covariant bound to fit in quite nicely with this existing literature on understanding quantum mechanics in terms of epistemic restrictions. So obviously the alternative to the epistemic view is an ontological view, which, as I say, involves saying that the covariant entropy bound really is telling us about the true ontological number of degrees of freedom on a light sheet, rather than just about the amount of information we can extract from the bounding surface. So Busseau in particular does seem to hold what I would call a positive ontological view of the bound. He writes that the bound's simplicity, in addition to its generality, makes the case for its fundamental significance compelling. And also various other proponents of sort of traditional holography like 't Hooft also seem to be taking a fairly literal view of the bound as counting the real number of degrees of freedom in the region. Now, I don't think that the ontological views are ruled out by anything that I've said thus far, but I do think that the possibility of an epistemic account problematizes the ontological view in some ways, simply because once we realize that there's a possible epistemic explanation of the bound, one might be worried that in giving an ontological account of it instead, we are just mistaking an epistemic constraint for an ontological one. We're seeing that we can only get a certain amount of information about some region, and then just assuming that that is the total information content of that region, even though, at least on a realist view, it should surely be possible to say that there might be more information content than we external observers can access. So that, I think, is a potential threat to various ontological ways of thinking about the bound. And to resist the threat from the epistemic approach, I would suggest that a compelling ontological account of the bound would have to proceed by calling into question some of the ontological and metaphysical presuppositions that make the epistemic view seem compelling. So in particular, sort of harking back to my earlier comments about the mismatch between the ontological content of space-time on our intuitive conception of it and the amount of information we can actually get out of it, would perhaps lead to some kind of way of suggesting that actually maybe the ontology of space-time should just be made to match the evidence more precisely. Maybe we were just always outstripping our evidence in inappropriate ways, and it would be better to have a conception of space-time in which its information content is better aligned with the information we can get out of it. So that would lead to a sort of more principled way of arriving at an ontological view of the covariant bound. One way I think that could be done would be to adopt some kind of relational approach to physics. So if, for example, we say that all valid physical descriptions of systems must be relativized to some observer, you can then also say that all observers will be observing systems through a bounding surface, and since the physical description is relativized to that observer, it's sort of in an objective sense the case that the full description of that system must be encoded on the bounding surface through which the observer accesses that system. And so in that kind of relational view, it's kind of objectively the case that systems really don't have any more information content than can be stored on this bounding surface through which they're accessed by the systems to which the description is relativized. Another way to get a similar kind of picture would be, rather than having relativized descriptions, just try to reduce all of space or all of space-time to a single bounding surface somewhere. That's essentially what various holographic approaches aim to do. But because our space-time is not an ADS space, it seems unlikely that it's going to work to reduce all of space to a single spatial surface, but there is potential to imagine reducing all of space-time to some surface in the future or the past. So that needs further exploration, but I think there's possibilities to make an ontological account work in that kind of way. So to sort of sum up where we are so far, I've set out both epistemic and ontological conceptions of the covariant bound and given some reasons some idea of what those might look like. I think at this point, if this were the totality of the evidence, I myself would be leaning towards an epistemic conception of the bound. But things get more complicated when we start to think about gravity. So the reason gravity is important here is that when it comes to the covariant bound, the evidence for the bound is partly gravitational. So if our evidence for the covariant bound were entirely composed of standing outside of regions and counting the degrees of freedom, or if it were entirely thermodynamical, which similarly involves kind of looking at how information emerges through the bounding surface, then I think the epistemic conception of the bound would be very compelling and quite hard to resist. But the evidence for the bound is also partly based on our understanding of gravity. So in particular, well-known proof of the bound is given by imagining entropy as being something like a local fluid and showing how that integrates over various regions of space-time, and combining that understanding with general relativity leads to a fairly general proof of the bound, which can be expected to hold in most regimes where this idealization of entropy as a local fluid is valid. So in particular, the gravitational effect that is often relevant to explaining the bound is what's known as the focusing theorem, which says that rays of light or other similar systems which carry energy will eventually come closer together and converge in a general relativistic space-time. And as Busso puts it, the focusing theorem is really important to the covariant bound. It certainly would not work without the focusing theorem. The idea here is that, as he says, entropy costs energy, energy focuses light, focusing leads to the formation of caustics, i.e. intersections, and caustics prevent light sheets from going on forever. So the reason that light sheets typically have a finite information content, and the fact that this information content turns out to be less than or equal to the bounding surface, is very closely tied to the focusing theorem. So given that the evidence for the covariant bound seems to be closely related to the focusing theorem, that seems to make it a little bit more difficult to take an epistemic conception of it, because gravity and focusing seem like very objective, observer-independent features of our reality. If anything is objective, surely it is gravity. So it seems less convincing to give an epistemic account given this close connection between the covariant bound and gravity. Indeed, it seems quite straightforward to argue that at least some of the phenomenology of gravity could be derived from the bound. At the very least, you can certainly start from the bound and make an argument to the effect that there must be something like the focusing theorem. And indeed, Ted Jacobson has quite a famous proof where he tries to derive the Einstein equations from an entropy area relation. Jacobson isn't using the covariant bound in that proof because this proof was arrived at before the covariant bound was suggested. But nonetheless, I think there's a quite straightforward way of sort of rewriting Jacobson's argument so that it is an argument for the Einstein equations from the covariant bound. I go through that in the paper. I think the proof has some weaknesses and holes, but nonetheless, it gives at least some indication that there is potential to argue for the Einstein equations from the covariant bound. So if you really were to say that you think the covariant bound is just an epistemic effect related to our ability to get information out of space-time, that kind of argument would then potentially have to lead you down the path of saying that focusing or even the Einstein equations are in some sense also epistemic, which seems, at the very least, to be a pretty extreme position to take. So obviously, it's quite important then in that connection to try to understand whether we should think about the entropy bound as explaining gravitational phenomena or vice versa. So Churko et al. Have a discussion of this question, and they argue, they criticize Jacobson's argument on the grounds that it is circular because they think that the entropy area relation used in his proof is itself explained by gravitational effects, so it would be circular to then use that entropy area relation to derive the existence of gravity. So their argument for this is to say that the entropy area relation should be derived from a quantum field theoretic calculation, which gives for the entropy across some region across some surface, S equals N A over L squared, where A is the area of the surface and N is the number of different species present. And they further argue that when you take into account gravitational effects, then the N cancels out and we end up with an entropy area relation, which is independent of what you say about the number of species present. So they say you only get a universal entropy area relation if you presuppose some gravitational effects. However, I think this approach to the question is kind of begging the question. Someone who thought the entropy area relation was universal presumably would just not agree that this is the right way to arrive at the entropy area relation. Indeed, if you think that the entropy area relation is universal, then instead of deriving this cancellation from gravity, you can instead say the entropy area relation implies that gravity must have the effect that this number cancels, because we know that this relation has to be universal. So if you take a sort of broadly fundamentalist attitude towards entropy area relations, you are not compelled to say that cancellation is due to gravity. You can just say it's the other way around. So I don't think that this argument by Churko et al. Kind of settles the question as to whether which direction the explanation goes in. And indeed, I do think there are some reasons to think that explaining things in terms of the entropy area relation is a better explanation, because as Rousseau has emphasized in various places, in order to try to derive the entropy area relations and the covariant bounds from gravity, you have to invoke a large number of different kinds of gravitational phenomena in different situations. Whereas if you start from the entropy area relation, you can derive all of these different phenomena from this one quite simple universal conjecture. So it's going to depend to some degree on what you take to be a good explanation, of course, but I think there's at least a case to make that the explanation starting from the entropy area relation is simpler and more unifying, and thus it would, I think, be premature to just assume that we have to derive the entropy area relation from gravity and not vice versa. So therefore, although I am hesitant to go down the route of suggesting that effects like focusing and gravity could be epistemic, I want to sort of again suspend that disbelief and try to understand what it might look like if we do think that the covariant bound is epistemic, and we think that things like focusing are in some sense a consequence of it. So the first point to be made is that although that is quite a weird position to take, it's not as bad as one might think, because the fact that if indeed this argument shows that focusing is in some sense epistemic, that would not mean that it's subjective. This sort of dichotomy is quite familiar from discussions of entropy and thermodynamics. The fact that entropy in thermodynamics is in some sense observer relative doesn't mean that it is imaginary or subjective. There are real objective facts about the limitations that observers have in terms of their interactions with systems, which define the correct way of describing the entropy for each observer. And similarly, in the case of focusing, if it is the case that only a certain amount of information about a system can emerge through its bounding surface, that is an objective fact about reality and not just an illusion. So although there would be something more epistemic about gravity in this conception, that would not be the same as saying, oh, it's all subjective, none of it is real. So let's therefore try to imagine what it might look like to use epistemic limitations on inaccessible information to give illusory gravitational effects. So here I'm sort of slightly altering an argument due to Susskind back in the early days of discussion of holography. So we imagine here some kind of screen with area A and an object behind the screen with area A prime, and we imagine that the information content on the surface of that object with area A prime saturates the bound, so it's proportional to the area. So we can then imagine sort of great rays of light coming away from that object and approaching the screen. So if gravitational focusing does not occur, then the area element on the screen will be smaller than the area element of the object, and thus, since the bound is saturated on the object, then if the bound on degrees of freedom on the screen also holds, that means that not all of the information from that object will be able to pass through the screen. So there's a case here, I think, to be made that in some sense the perceived area of that system is going to be less than the real area, because perceived area plausibly has something to do with the number of degrees of freedom we can access about the surface. And so if we don't get all of the degrees of freedom passing through that screen, we're going to have a distorted view of the area of the actual object. So obviously, Susskind doesn't make this argument very precise, and one would have to develop it further to sort of see more clearly how that works. But I think there's at least a case to be made here that we can understand how it would be that epistemic limitations on external information could give the external observer the perception that something like gravitational focusing has occurred, even if it actually hasn't, because not all of the information will pass through if there's no focusing happening. The alternative, of course, would be to still say that the covariant bound in some sense explains focusing, but take an ontological approach to the covariant bound, which would give a more ontological account of focusing in terms of surfaces. So, for example, if you would adopt, as I briefly suggested earlier, some kind of ontological approach to the bound where we say that light sheets are in some sense just alternative representations of bounding surfaces. For example, that would be the case in a relational view where the information content of a region must be exhausted by what's written on the surface because the observer can only access what's on the surface. Then you can kind of straightforwardly argue that geodesics just have to be focused by matter, because if they were not, then light sheets would contain more information than their bounding surfaces, and that would be impossible if light sheets are just alternative representations of bounding surfaces. So if you want to take this kind of strong view where you are making a clearer attempt to match up the ontology of space-time with the epistemology of what we can find out about, then some kind of ontological argument for focusing seems to follow in a fairly direct way. It's worth noting that the derivation of various gravitational phenomena from the covariant bound wouldn't necessarily use approximations. In particular, it relies on approximating entropy as being treated as something like a fluid. So those effects then would not be sort of fundamentally correct. Rather, they would be effects that emerge in some appropriate limit as those approximations become true. And that would therefore make gravity into something like an approximate emergent phenomenon. So this kind of approach, I think, would fit in quite nicely with the existing literature on people trying to think about gravity as potentially being emergent. So that's pretty much what I had to say. Just to sum up, I think that both the ontological and epistemic conceptions of the bound have arguments in their favor. I am undecided which way I would want to go, but it does seem to me that whichever way you go, this question potentially has important consequences for how we should think about space-time, and this ties in interesting ways to the kinds of questions we're trying to confront in quantum gravity in terms of understanding the ontology of space-time, and particularly how that relates to all this talk of surface in quantum gravity. So I don't know the answer to this question, but I do think it's an important question, and I would love to hear either your questions, or if you know the answer, I'd love to hear what you think the answer is. So thanks for listening, and we should see if there are questions.
Should we get rid of the?
Yeah.
I'll stop the share then. Okay. Guess I'll leave it like that. Okay. We usually let the people in Geneva go first if they have questions there. I don't hear you.
Okay. I have a question. Do you hear me?
Yeah.
So, one thing I'm not fully clear about, but I would like to know more, is what the idea of the covariant bound is supposed to be. So this is a research program, or could be used as the base for a research program that derives from certain fundamental assumptions about entropy, the gravitational phenomena. So the first question is whether that's right. And the second question would be what kind of gravitational phenomena one would derive from that, like a Schwarzschild solution or something like that.
Yeah, so I mean the entropy bounds would The original goal was not to derive gravitational phenomena. The entropy bounds are a sort of were a result which came originally from generalizing the Bekenstein-Hawking entropy. It wasn't postulated to achieve something in particular. It was just postulated as this seems to be true. If the Bekenstein-Hawking bound is correct, then there has to be some kind of bound on the entropy of other regions of space-time, and this bound doesn't appear to be what we would expect to be. That's striking and interesting, and what does that mean? And that has sort of partly led to and fueled the growth of various holographic theories. So that's one important contribution it has made. But then conversely, there have been some people suggesting various approaches to deriving gravitational phenomena from this idea. And so the proof by Jacobson that I mentioned is the most famous example. That this was prior to the formulation of the covariant bound. So he wasn't thinking in precisely those terms, but he does use an entropy area relation of the same kind of form as the covariant bound. And he argues that you can derive Einstein's equations from that entropy area relation. And obviously then from Einstein's equations, you can derive any particular solution of Einstein's equations. So if Jacobson's argument were right, that would be a very striking fact that all of gravity comes from an entropy area relation. I think there are still weaknesses in Jacobson's argument, so I wouldn't fully endorse the argument, but it is at least an interesting indication that there's some quite strong relation between entropy area relations and gravity. And in particular, even if Jacobson's argument doesn't work, what I do think is sort of undeniable is that you can certainly derive from the covariant bounds a necessity for something like a focusing theorem. So that's at least one big part of the phenomenology of gravity, which does seem to follow in an uncontroversial way from the covariant bound.
Yes, so thank you very much. I'm aware of Jacobson's work, but the question would then be, what does the covariant bound add or contribute beyond Jacobson's work? That's not so obvious. Is it just more like a more general, how should I say, incentive to pursue holographic approaches to understanding gravitational phenomena in terms of boundary phenomena and using conformal field theory like in ADS-CFT?
I think that the key point is that the covariant bound seems to be true. Like the evidence suggests quite strongly that at least in many regimes the covariant bound is definitely true. And so the question that remains open is, why is it true? What does it mean, and what does that tell us about space-time? Because as I sort of tried to say, I think the fact that we seem to have this relation between the entropy on light sheets and the entropy on surfaces seems to me very striking and quite surprising, and we don't yet, I think, have a good understanding of why that relation should hold in this particular way. So it may of course be a complete red herring, but it sort of seems that there's some interesting connections here with various questions going on and what we talked about in quantum gravity and how we should understand space-time. So I think getting clearer on what the covariant bound means, what it's telling us about space-time, and what that means for things like quantum gravity seems like a worthwhile project.
Yes, thank you very much. So, Niels?
Yeah, just to the Nicholson thing quickly. Thanks, by the way, for the talk. So you mentioned some holes. Are these obvious to you right now, the holes in the derivation, or there might be some holes in there?
The holes in the Jacobson derivation?
Yeah, in your version, right? I think at some point you talked about holes, possible holes.
Yeah, what I did in the paper was to just rewrote Jacobson's derivation in the language of the covariant bound. So it is basically exactly the same process, like different language. There are limitations to it. I think the biggest limitation in my view is that it requires a bunch of quite specific conjectures that come from quantum field theory in terms of the amount of entropy in various regions of space-time. And it's not totally clear why you should accept those specific values coming out of quantum field theory in this derivation that's supposed to be a sort of general claim about space-time. So I would like to understand better whether you really need to get these numbers from quantum gravity or whether you could get them from somewhere else. there's also sort of limitations in terms of the modeling of entropy. You have to make assumptions about sort of continuity and locality of entropy, which we know is not necessarily true in all regimes. So again, it would be nice to understand the extent to which those assumptions can be lifted, or how things change if you look at regimes in which those assumptions aren't valid at all.
Yeah, cool. Okay, yeah, thank you, yeah.
So I think for the time being, we don't have a question here. Maybe we should move to Chicago and get back here if there's further questions.
Yeah. Also going to say there are some people watching on YouTube, so you can put questions in the chat there that I would read out. It's actually, you look like you had questions.
I do. So Emily, this is really great because this is something that I've been thinking about for a long time as well.
Right.
And since you seem to be open to reactions to the question you posed, I hope you don't mind me putting my reaction out there.
Please do, yeah.
So I completely agree with you about this observation that the pairing between epistemic and subjective, especially in discussions about entropy, should be decoupled. Yeah. But here's where I disagree. I think that's the case for both the covariant postulate and the surface postulate. Mm-hmm. And what you're calling the epistemic and ontological division, for me, the work is coming from somewhere else. And it's based on something you very much said when you were cashing out what you meant by epistemic accessibility, where you said that, it's assumed information flow is through local interactions. Yeah. And to me, local is the key premise where the surface postulate holds on to causality, and the covariant postulate denies causality. I mean, that's the MO of holography in what you call the positive ontological sense, is that they deny information transfer through these local interactions.
I think I agree that's true of traditional holography. I'm not convinced that's true in the covariant formulation of the bound, because the light sheet is related in a light-like way to the surface. It's perfectly possible to have local causal transfer of information from the light sheet through the surface. Right.
So that is part of my question. But it sounds to me so I think, I would love to hear your thoughts on that. But if I may just kind of continue with this line of thought, what you were saying about trying to reconcile the two, to me, sounds more just like the surface postulate, where you hold on to the premise of causality because you're maintaining, the local interactions for the information flow. And to me, that's ontological too, in the sense that you mentioned with Rovelli and Smolin, where they noticed that the interior degrees of freedom that are not subject to the bound are doing important work in the physical description, let's say, black hole evaporation. And so I wanted to understand more. To me, it sounds like your position that you're leaning towards is just very straightforwardly that, as opposed to what I take to be the other camp that denies the premise of local information transfer. And I don't think they can be reconciled in that sense, because you either keep that premise or you deny it. To have both would be a contradiction. So I would love to kind of understand more what you mean by you're reconciling both of these two postulates. And then I guess if it kind of fits in with your explanation, I'd also love to learn a little bit more about in what sense the covariant entropy bound, where locality, because obviously the light sheet formulation is respecting causal relations to some extent, but on the other, if you say that's truly the ontological bound of the interior volume of the region that you're looking at, that has to be a non-local relation to basically collapse, a three-dimensional volume in terms of its information content into a two-dimensional surface. Like, there's going to be non-local, right? There's going to be a non-local distribution of information somehow of that picture.
So again, I don't think that the covariant bound does indicate a non-local picture in that way. Indeed, I think one sort of interesting thing to follow up on is what holography would look like if it's formulated more along the lines of the covariant bound than the strong bound. Because I agree, if you're thinking about the strong bound and you're mapping a 3D region of space to its bounding surface, that does look like a highly non-local description. But because the light sheet is projected behind the surface along light rays, there's nothing to stop you from saying that the information content on the light sheet just gets communicated through ordinary local processes to the surface. And indeed, I think, to me, this looks like it's pointing towards what Niels calls like holography without holography, which is when he refers to, if I understand correctly, correct me if I'm wrong, Niels, but the idea here is that you have holography where some actual region of space-time is reduced to some other actual region of space-time via like actual communication of information between them. And so the covariant bound looks to me quite friendly to that more physicalist conception of holography, where the information content of the region matches the surface, not because of sort of magic non-local connections, but because there's an actual transfer of information between them. So because I was focusing on the covariant bound, the conceptions I suggested of the epistemic and ontological views here, I was in both of those kind of intending to be imagining a local transfer of information only. So the question then is, should we think that if we're imagining this kind of local situation, that it's really the case that there are more degrees of freedom on the inside that we just can't find out about, or should we take it that we were just mistaken about the ontology of space-time and we should have a sort of closer link between surfaces and bounding surfaces and the interiors, which would in some sense perhaps explain in a potentially fully local way why we have this relation. So yeah, I don't view either of the views I presented here as necessarily assuming any kind of like non-local information transfer, because the covariant bound has this nice feature that it can all be understood locally.
So I have a follow-up question to that. So given that, even after Bousseau proposed the covariant bound, there's been a lot of work in what you call the positive ontological view that very explicitly admits to non-locality. And I'm thinking especially in the context of black hole evaporation, how to get the information out, essentially. So how do you then square, these views, which are self-proclaimed as advocating for non-locality, and they tend to be string theorists, which have non-locality built into the ontology from the get-go, and the covariant.
And I want to distinguish between non-locality and like instantaneous transfer of information. Just I'm not an expert on string theory, so I don't know well this kind of non-locality they get there, but I would think that even in string theory, certainly in the appropriate emergent limit, you would have to get that information transfer as only local, otherwise you wouldn't be empirically adequate. So even if you're willing to postulate some kind of, I think the whole story I've told is certainly entirely compatible with non-locality in the sense of Bell correlations, because we don't transfer information using entanglement. I don't know whether it's the case that you have real superluminal transfer of information in string theory, but even if you do, you would certainly have to get to some limits in which information transfer is local, and then the whole story I've told would still apply in the appropriate limit. So yeah, I don't think the story relies on locality. I think it relies on local information transfer, which does seem to be true in our universe, whereas locality, as I understand it, in the most general sense, doesn't seem to be true in our universe.
May I have one more?
Yeah, sure.
So do you think that for, I guess, the covariant story and, whatever underlying non-locality there might be in the strong holographic picture, you're saying that there has to be some sort of, appropriate limit in which the two pictures converge. And I was just wondering, because it seems to me that that's precisely the controversy, where where you should recover locality for empirical adequacy. And I know one of the main challenges of resolving the black hole information loss paradox, especially if you are in the strong holographic camp, is basically not violating local information transfer in the way you're talking about it. In these low energy regimes in which we think, in which space-time has presumably emerged with, the causal structure that we want it to have. So I know that's been an ongoing challenge in which that hasn't really been accomplished. So do you know if the covariant entropy bound and the kind of live holographic proposals on the table, do you know if actually because of this challenge they are in fact compatible or not? I'm just
so I'm not an expert on holography either. I try to learn more about it, but a lot of holographic proposals that I look at seem to be more compatible and influenced by the strong entropy bound rather than the covariant bound. ADS-CFT often seem to be understood in terms of an interior and a bounding surface rather than a covariant story. And that would fit in with string theory because it's often formulated in that 3+1 way. So I would like to see more development of holography in a direction that is better aligned with the covariant bound. And I think with a so-called covariant story like that, there's less need for strange non-local effects. But obviously that would have to await further development of that. I would also say that I am perfectly happy to accept non-locality in general, and I'm also actually not that concerned about non-local information transfer if it occurs only in sort of specific cases which are not accessible to us, or if which can't, in particular, I would like it to occur only in regimes which can't be used to create like causal paradoxes. So I would be perfectly at peace with the possibility that we do get non-local information transfer in some certain extreme regimes, provided that we are able to recover the appropriate macroscopic limit of our ordinary experience where there isn't non-local information transfer. So I'm not sort of opposed in principle to non-local information transfer. I just take that as an empirical observation that in the regimes we're familiar with, there is no non-local information transfer.
Any more?
Oh, I can go on. That's why
Maybe I'll take it. So thank you. So this was great, and I'm learning a lot. So which also means that I don't feel all the pieces are anything like in enough of an order to give a totally coherent question. So, but maybe answering this will sort of help. So, when you started talking about this, and you were talking about Bekenstein, of course, I'm thinking like black holes. But then, it's not. I mean, it depends what picture you have of black holes. On gravity theory, but it's not kind of obvious that you should think of the boundary of a black hole as something that's preventing information coming out at all, right? The picture's physically very different. There's stuff going in, and then, right? I mean, maybe it doesn't come out at all. There's sort of models where even if there's Hawking evaporation, it still all stays in there, and we have it all in. So part of the question is sort of, maybe you can relate what you're saying to that, but the sort of bigger question was to try to understand sort of the logic that it sort of became clearer when you were talking about Jacobson at the end, that this isn't so much about what's going on in a black hole and black hole entropy. It's more about how gravity and sort of information ideas are related. Is that about how I should be framing sort of things in my mind?
Yeah, so the black holes here were mostly relevant to explain the history of the covariant bound, but we now have reasons completely independent from black holes to think the covariant bound is right. We have general proofs for both the classical general relativity and some areas of quantum field theory to show that this bound is like pretty universally true. So, through most of this paper, I was mostly just trying to put black holes aside and say, if the covariant bound is true of just arbitrary regions of space-time, how should we understand that, and what does that tell us about space-time as a sort of general notion? And I think it's for the arbitrary regions of space-time case that the epistemic interpretation becomes perhaps more relevant because, as you say, in the case of black holes, nothing is coming out anyway. So we're not, whatever we know about the inside of black holes is not from getting information from the surface. But I think this sort of quite powerful observation that various people have made that when we study ordinary physical systems, we are interacting with them through bounding surfaces. Perhaps that role of bounding surfaces in the epistemology of space-time and of physics has not yet been given its due weight in terms of how that limits what we can find out. And so,
but the quotes you, just to make sure I'm clear about, I think the quotes you gave about, and you're saying, oh, this person seems to be epistemic.
Yeah.
They were generally talking about black holes in those cases, though, right? So it's not quite so clear what they would say about the general case.
The one person who has discussed this stuff explicitly in terms of the entropy bounds is Lee Solon, it's a really nice paper where he seems to be arguing what I call a positive epistemic view. The other people I was mostly looking at their views of black holes and extrapolating that since the entropy bounds are supposed to be generalizations of the black hole entropy, plausibly they would want to say similar things.
Okay. Sorry, but I interrupted you to ask that follow-up.
I forgot what I'm going to say, so it probably wasn't very important.
Okay. I mean, the last part of the original question was, so I should be thinking of this as, this is sort of a question about, so we have there's different kinds of assumptions in this field. There's GR, there's field theory, there's sort of postulates about sort of entropy, sort of information theoretic ideas. So in a sense, the big question is what are the logical connections between all these? And then, well, if you now read some ontology into that logic, which thing is more fundamental and how do things end up looking, something like that?
Yeah, I think it's sort of nicely illustrated by the Churko and L versus Jacobson debate, where Churko and L sort of assume that correct explanation of this state must be in quantum terms of quantum field theory. What else could it be? And I think, having spoken to Jacobson, it seems like the response is just that's the wrong direction of explanation. You shouldn't assume that's the right direction of explanation. You're sort of ruling out this other kind of explanation by fiat, by doing that. And I think it's in this kind of case where perhaps our normal understanding of what explains what is so far from our intuitions that it's hard to have a sort of obvious answer to that question. And there's this sort of complex, every time we have these relations of interderivability, there's this complex dilemma of, what explains what, does it even make sense to us which one explains what direction does it go in? And so I think, part of answering what's going on here is trying to understand how give a sort of framework for posing some of those explanatory questions by reducing it down to this question about are the origins of the covariant bound out there in the world, or are they about information transfer through services, which seem to lead to different ways of answering these explanatory questions.
Okay. Yeah, good. No, that's really helpful. That helps put a lot of the pieces. Yeah, follow. Okay, good. Did any have any questions come up in Geneva? We'll let Niels go.
I think you very nicely outlined what, of course, different reading options there are for the topic bound, and also what is reason for Jacobs. But can you just ask one more time again? So, what is your preferred understanding of Jacobs in light of this reformulation using the entropic bound, and has this changed with respect to your prior understanding of Jacobson, or would you think basically all the different readings you've had for basically all the different readings you now can offer could also be offered to the rich information? Probably not, right? And just back on, I mean, is there really like a third way you have of understanding Jacobs in light of this?
Yes. So I mean, Jacobson's original proof, as I say, is in terms of an entropy area relation rather than an entropy bound. And it's somewhat hard, I think, to tell from Jacobson's original paper exactly how he interprets that entropy area relation. And having spoken to him about it, I'm still not totally clear how he interprets the entropy area relation. I think he doesn't think of it as being a bound. He seems to think of it as being just a fact about the entropy associated with or across a surface. So he seems to be to link his views quite tightly to what I call the surface postulate, where these relations apply just to surfaces and not to interiors. But I think a very similar version of his argument can still be made if you're thinking about the interiors as well. So I think it's somewhat, even if you like his proof in general, I think it's somewhat inclusive how you should interpret that in terms of what the entropy is the entropy of and where it comes from and what it is describing.
I mean, if I just look at Jacob's 995, I think very natural attempt of understanding is in terms of kind of that the gravitational field somehow stands for collective matter field or so, which gets expressed through something which behaves locally thermodynamic with some other equation, and then globally you would maybe think that it's something hydrodynamic or so if you want to go this route. But now with the entropic bound, I'm personally pulled more towards the epistemic. I mean, still, data set, I guess, as you clarifying in the paper. Do you have the same inclination to be pulled more towards this kind of general understanding of modeling systems through the split of observer and on one hand system on the other side, which you said also suggested. I mean, you also suggest in other branches these days. I mean, do you have kind of more systemic leading up all in with these picture Jacobs, or you don't want to take a stance there?
Is my answer. I guess I think one of the at times Jacobson does seem to want to suggest that the entropy area relation he's dealing with should come from a quantum field theoretic calculation of an entanglement entropy. And I think the problem he runs into there is correctly picked out by Churko et al., who I think make a compelling case that quantum field theoretic calculation isn't going to give you the right result without building gravity in from the start. So if that's where the area relation comes from, I think the charge of circularity is reasonable. But I think it is open to Jacobson I don't think he would want to do this, but it would be open to Jacobson to take a kind of epistemic approach and say, no, I think of this bound as being a limitation on information passing through surfaces, and thus I think of it as being a kind of general principle that comes directly from the epistemology or ontology of space-time and not necessarily from a specific quantum field theoretic calculation. So I think if he's going to get around that charge of circularity, he needs to tell some story other than just that the entropy area relation comes directly from field theory.
Is the chat a question, or just that's not a
No, it's not a question.
No, it's not it was someone, Brad was saying goodbye. So it's actually, yeah, we have time for one more question, I think.
So I'd be interested to hear a little more on why you're leaning towards the view that, ontologically there could be many more degrees of freedom than what is accessible to, an observer, outside a given boundary.
Yeah.
And in doing so, I would really appreciate clarification. If I understood correctly, you said, although you're open to both, you think a major vulnerability of, just postulating the covariant bound as, a full stop upper limit on degrees of freedom seems to work only in ADS CFT correspondence, and we don't really know if it'll work outside that context. And I was confused about that worry, because it seems that the covariant bound, is applicable to other space times as well. So I would just appreciate kind of a little more, holistically on where your predilections lie and what you think the strengths and weaknesses are.
Yes, I mean, the concern here is that once you have what looks like a sort of compelling story about why we would naturally end up assigning this number of degrees of freedom to regions of space-time regardless of how many degrees of freedom there really are due to our own epistemic limitations. It then looks as though a position which says no, that really is the total number of degrees of freedom is somewhat poorly justified, because all the evidence one might invoke to argue for, yes, that is the total number of degrees of freedom, can be reinterpreted as, well, no, that's just an artifact of our epistemic limitations. So it seems a little bit hard to come up with a compelling justification for your view that this is the real total number of degrees of freedom, unless you're going to do something which involves kind of rejecting the presuppositions that make the epistemic story compelling. And so that was the thought here, that I think a compelling ontological view would have to do more than just postulate that this is the number of degrees of freedom. It would have to tell some alternative story about like the ontology of space-time, which would make that view compelling. For example, by adopting some view in which there's a really tight link between light sheets and their bounding surfaces, and perhaps bounding surfaces are just alternative representations of light sheets in some way. So one way to do that would be via the kind of relational approach I discussed, where physical systems are relativized to observers, and so the full description has to be on the bounding surface, or alternatively some kind of quasi-holographic description where everything is really reduced to some surface somewhere. And the comment about ADS CFT there was just that the only way we know how to do that concretely right now is in terms of an ADS CFT description, which doesn't seem to apply in our actual universe. I think they're interesting because the covariant bound has this feature that it relates things in a light-like rather than a space-like way. I think there are possibly interesting ways that one could do holography differently using that sort of light-like connection rather than a space-like connection. But those have not yet been fully developed. So at the moment, ADS CFT seems like the only good example we have of what it would look like to reduce all of space or space-time to a single bounding surface.
1 minute.
Okay. So for me, I think, I won't necessarily go into the motivation now, but I think one of the main questions to ask, and something that I've started thinking about, and I was wondering if you thought about it too, you mentioned, we need to close the gap between, at least historically where it started, between thermodynamic entropy, which was the inspiration for the entropy bound, and information theoretic entropy. And to me, that link is statistical mechanics. Like, we need a good story of reduction.
Yeah.
So have you thought about, both of these kind of overall positions, what their story of reduction is, and has that informed your predilections?
Yeah, I think in both cases, it's not straightforward to give an explicit reduction, because in statistical mechanics, we have a fairly good grasp of what state space looks like, so we can, at least in outline, say what the reduction looks like. And certainly in the case of an arbitrary region of space-time, and also to some degree in the case of a black hole, we don't have much independent grasp of what the state space is. And so without knowing what that state space is, we can't explicitly affect a reduction. So presumably on either of the ontological or epistemic accounts, one would imagine that there would ultimately be some reduction of the story about the entropy to some kind of statistical mechanics of space-time or of black holes. And there have been attempts to do that in the case of black holes. They're somewhat speculative and limited, but there's some progress there. In the case of general regions of space-time, it seems like you'd need a full theory of quantum gravity to do that, so that's quite a complex task. But certainly one would expect that some reduction would be possible at some point.
Okay. Any more from Geneva?
No, I don't think so.
All right then. I think we will say thank you. That's about the time we said anyway. Thank you so much, Emily. That was great.